To generate interpolating surfaces for other subdivision schemes, we need a method of determining the position and the normal at a set of points on the limit surface. Because the surface is the result of repeated application of a subdivision step, we can analyze the behavior of a small neighborhood of points as they converge to the limit surface, in order to determine the surface properties at the point of convergence. Subdivision surfaces are a powerful and a useful technique in modeling freeform surfaces. They can be widely used in many fields such as computer-aided design, graphical modeling, computer animation, medical image processing, and so on. The Catmull-Clark subdivision surface was designed to generalize the bicubic B-spline surface to the meshes of arbitrary topology. In Catmull-Clark scheme, an initial control mesh is refined by adding new vertices, faces, and edges at each subdivision step. In the limit, as the number of subdivision steps goes to infinity, the control mesh converges to the Catmull-Clark limit surface. Thus, Catmull-Clark scheme is an approximation subdivision scheme. I will consider the use of subdivision limit surface a wildcard of sorts, meaning it can solve some elusive problems that might look like black magic to unfamiliar people, or the solution simply be faster, smarter, lighter, etc. It is a very simple concept, and thanks to OpenSubdiv and the integration within Houdini, that makes it very easy to use. We will look at some practical examples that you can use in your day-to-day work. With that said, see you guys in the next lesson. Each quadrilateral face in a Catmull-Clark control mesh corresponds to a single bicubic patch, except for quadrilaterals that contain an extraordinary vertex. These extraordinary patches containing one or more extraordinary vertices, are actually composed of an infinite collection of bicubic patches. We can get a list of patch IDs in a subdivision hull using the OST patches function. It is a nice candidate to be our first function into the world of OpenSubdiv in VEX. We will use a single polygon as the input geometry. So create a circle with 3 divisions. Subdivide this polygon. Split and scale down each polygon. And color them randomly. What we are looking at are basically the OpenSubdiv patches. Now create an attribute wrangle, call OST patches, and store the resulting array as an attribute. I also store the array count. As you can see, we get 3 patches for a triangle. But watch what happens when we have a quad. We don't get 4 patches. Instead, we only get 1 patch. Why is that? Catmull-Clark subdivision behaves nicely with quads, and as such, using them yields a smoother surface. By the nature of the Catmull-Clark subdivision algorithm, a quad will yield a single patch, unless they contain an extraordinary vertex. As you can see in the last 2 images, the central quads produce more than 1 patch, even though they are quads. That is because the vertex at the very center of the geometry is an extraordinary vertex, and as such causes the quads that contain it to produce multiple patches, rather than 1 patch. A pentagon produces 5 patches. And a 10-sided polygon produces, well, 10 patches, and so on. And with that said, see you guys in the next lesson.